part in this chapter, we're going to quickly go through 5.3, where we talk about what binomial probability distributions are, and we will be using StatCrunch to do our calculations in that section. And then in 5.4, it just talks about the mean and the standard deviation for binomial probability distributions, and those are calculations that are relatively easy to do by hand. So let's go ahead and look at the definition of a binomial probability distribution. What happens when something is binomial means that there's only two categories. So it's yes or no, men or women, black or white. If you've got more than two categories, it is not a binomial probability distribution. And there has to be a fixed number of trials. So in other words, you have a sample of a certain size. Those trials must be independent. So think of it, it'd be like drawing marbles out of a bag when the marbles are replaced, so that the outcome of one trial doesn't affect the outcome of the following trials. So that's very important. And again, this is a very special category of discrete probability distributions. Now there's also a Poisson distribution that's in section 5.5. We are not going to talk about that. We are only going to talk about the binomial probability distribution. So again, two categories, success or failure. We might look at a sample of 25 vehicles. Is it a pickup or not? It's a success or a failure. And then again, the probability needs to remain the same in all trials. Number 4 and number 3 are tied together. Now, what happens when we do these calculations? If we have a very large population as compared to the sample size, so if our sample is no more than 5% of the whole entire population, we do treat them as being independent. It's a very good estimation and it makes our lives easier. Now here are some things that are important. So the probability of a success is lowercase p, and I usually use a cursive p to stand for this because it is actually italicized. The probability of a failure is 1 minus the probability of a success, or it's q. So we're going to talk about p as the probability of success, q as the probability of failure. The lowercase n tells us how many trials we have, how big is our sample, and x is the specific number of successes in the trial. And then P of x talks about the probability of getting exactly x number of successes among the trials that we're going to look at. Now, when we talk about x, that is the value of the success. When we talk about p, that is the probability of the success. So it's very important that you keep your frame of reference to be the same. And again, when the number of your sample, lowercase n, is less than 5% of your population, uppercase N, then you can sample even without replacement. Now there are different methods to do this. There's the formula, there's technology, and there's a table in your book. We are going to focus on technology. I'm going to show you the formula. If you're interested in it, you can go through how it's derived. If you want to look in your book and discover how to use the table on your own, feel free to do that, but we are going to use StatCrunch to help us with this, because our goal here is not to be able to do the calculations, but to be able to interpret our results. So here's the formula. So the probability of x is, and this is n factorial, And a factorial is that number times all the numbers that are smaller than that. So 4 factorial is 4 times 3 times 2 times 1. A factorial can get very large as we go forward. If you have a scientific calculator, you do have this exclamation point key on your scientific calculator, but again, don't worry about doing this by formula. But it is important to know that n is the number of trials, x is the number of successes, p is the probability of successes, and this should be a lowercase q, is the probability of failure. And then just by definition, 0 factorial is 1. So here's an example. Given that there's an 85% probability that any given adult knows of Twitter, use the binomial probability formula to find the probability of getting exactly 3 adults who know of Twitter when 5 adults are randomly selected. So here is the number we're going to select, how many successes we have, our probability of success, our probability of failure, and we want to know the probability of exactly 3. So let's take a minute and let's look at the formula. And the first part of our formula is the number of outcomes with exactly x successes among n trials. And the second part of our formula is the probability of x successes among n trials for any one particular order. Now, these probability formulas, equations, are in the part of chapter 4 we didn't cover. So if this looks like a foreign language to you, it probably is. That's okay. Just know there is a way to do it by hand, but we're not going to do it that way. Here is what the formula would look like. So we'd have 5 factorial, which is 5 times 4 times 3 times 2 times 1. And we have our p to the third power. We have our q to the 5 minus 3 power, which is the second power. This is going to be 2 factorial, and this is going to be 3 factorial. So this first fraction reduces to 10. We have 0.85 to the third power, 0.15 to the second power, so we get there's a 13.8% chance that exactly 3 adults out of a sample of 5 have heard of Twitter. Okay, that's how you do it by formula. Again, I just wanted to show you the process. It is not going to be something that you need to do. We are going to use StatCrunch. And in StatCrunch, you're going to click on Stat, Calculators, and then Binomial. So let's look at that last example, and remember, when we want our binomial calculator, we go to Stat, Calculators, Binomial, and let's bring this over so you can see it. And in this case, we had a sample of size 5. We are interested in 3, and our probability was 0.85. So again, we're looking at samples of size 5. Will we have exactly, I need to change that operator, exactly 3 adults out of 5 who have heard of Twitter is 85%, and we get a probability of 0.138, and that's exactly the same thing we did when we did it by the formula. Let's look at a problem next out of the book. Let's look at the binomial distribution calculator. So we're going to go into Stats, Calculators, and you see the second one down is binomial. And now what you're going to do is you will put in
You don't have to enter any data on the spreadsheet. What you're going to do is you're going to put your n in the n, the probability, and then you can do the other things. So for instance, it says that, and I'm looking at number 31 on page 243, based on a Harris poll among adults who regretted getting tattoos, 20% said they were too young when they got their tattoos. Assume that 5 adults who regret getting tattoos are randomly selected. Find the indicated probability. So first of all, our number is 5. And we know our probability is 20%, which is 0.2. Then it says A is find the probability that none of the selected adults say they were too young to get tattoos. So what's the probability that X equals 0? And I'm going to do compute. And I get that the probability is 0.328. So about 33% of the time, no adults out of samples of size 5 say they were too young to get a tattoo. If we look at part B, and it says find the probability that exactly one of the selected adults says that he or she was too young to get tattoos, we're simply going to change our 0 to 1. And we're going to press compute, and there we have about a 41% chance that exactly one person in a sample of size 5 says they regret getting a tattoo because they were too young. Now let's find the probability that the number of selected adults that says they're too young was 0 or 1. So then we would go X is less than or equal to 1, and you can see that's about a 74% chance. So translating that, there's about a 74% chance that 0 or 1 adults in a sample of size 5 say they regret getting a tattoo because they were too young. Now part D says if we randomly select 5 adults, is 1 an unusually low number who say that they were too young to get a tattoo? Well, we just already found out, let's go back, that about 40% of the time, one person will say that. So this probability is not small enough to say it's unusual. If it was 0.05 or less, we could say it was small, but it is not small. Something happening 40% of the time is not a small probability. So let's look at this and go on to section 5.4 and talk about the mean and the standard deviation for binomial distributions, because guess what? We want to talk about shape, center, and spread. So what we're going to do is we're going to find its mean. We're going to find the variance, but remember we usually are more interested in the standard deviation because we want to know where the center is and we want to know the standard deviation. Why do we do this? Well, the binomial distribution can be used as an approximation to the normal distribution, which is what we're going to talk about in chapter 6. So here's the formula. For any discrete probability formula, here are the formulas. For the mean, we take each value times its probability and we add them up. We find the variance, and the square root of that is the standard deviation. But for a binomial distribution, the mean is simply the number of fixed trials, so the number you have in your sample times the probability of a success. Your variance is your mean times your probability of failure, and then the standard deviation is the square root of that. These are numbers that we can find using it's usually in the problem, and these are calculations that are easy to do with a calculator. Now, one of the things that we need to be able to do is we need to be able to interpret the results. So we use the range rule of thumb.
Again, our usual values are the mean plus or minus 2 standard deviation units. Let's look at some examples.
370 adults. Our probability is still 20%. We'll go back and we'll get that equation for the mean, which the mean is n times p, and then the standard deviation will be the square root of n times p times q. So if p is 0.20, q is 1 minus p, which will be 0.80. So we can just do this simply with a calculator. So the question asks, find the mean and standard deviation for a number who say they were too young when they got their tattoos. So we know the mean will be 370 times 0.20, which will come out to be 74. So the mean of the number of people out of 370 who say they were too young when they got their tattoos will be 74. The standard deviation will be the square root of n times p times q. So that is going to be 7.7. And again, we're going to take our values out to one decimal place because our data, the number in our sample, was to the nearest whole number. So now it says, so this is A. B. For a randomly selected group of 370 adults who regret getting tattoos, would 90 be an unusually low or high number who say that they were too young when they got their tattoos? Let's look at our usual range. And that's still our mean plus or minus 2 standard deviation units. So we know on the high end it's going to be 74 plus or minus 2 times 7.7, and on the low end it's going to be 74 minus 2 times 7.7. So our high value is going to be 89.4. Our low value is going to be 58.6. And the number we're looking at, 90, is above our high unusual value. So since 90 is greater than our mean plus 2 standard deviation units, it is an unusual value. Let's call it unusually high. That makes sense? So you really don't need to use StatCrunch to do this because these formulas are pretty easy.
Done here is we've talked about the mean, variance, and standard deviation for any discrete probability distribution, and we've done it specifically for the binomial probability distribution. And we've talked about, is it unusual or is it usual? And we've used the same rules all along for talking about usual and unusual. If it's within 2 standard deviation units of the mean, it is a usual result. If it's outside of that, it will be unusual. Let's look at the active learning questions. Might want to do this one on StatCrunch. This is an expected value problem. You want to do this one on StatCrunch.